Today we're going to take a look at the last section, the binomial theorem and probability. But before we do that, we're going to jump a slide here. We'll come back to this one. But we're going to take a look at something we looked at last chapter, Pascal's triangle. And we're going to see how these combinations that we've been talking about relate to the triangle. So, let's turn on the Moby here. First thing we're going to do is I want you to try and type into your calculator 2C0, 2C1, and 2C2. And take a minute and I want you to see what you get. Hopefully you got 1, 2, 1. Now I want you to take a minute, type in 3C0, 3C1, whoops, that didn't turn out, 3C1, 3C2, and 3C3, and see what you get. You got 1, 3, 3, 1. So these combinations, they appear in Pascal's triangle as well. We have row 1, row 2, row 3, and it relates to the number we're choosing from, 0, all the way up to our total of 3. So we're going to be using this when talking about binomial experiments today. And what binomial experiments are experiments that have the following conditions. There must be only 2. So you're either flipping a head or a tail. It will rain or not rain. There's a fixed number of trials. Each trial is independent, meaning it doesn't affect the other one, and probabilities of each trial are consistent. So the way we set this up is we're going to use those ideas of the combinations, and we can find those numbers from our triangle if we don't want to use the combination key on our calculator. X is success, Y is failure, the number of trials is how we're choosing, and the one after that is the number of successes, okay? So it looks a bit complicated. You could rewrite it as NCS, trials, number of success. We could say P of S to your S times P of failure, your probability of failure, to the F, the number of failures you're going to have. So we'll take a look at a couple examples, and I think that will make it a little bit easier here. So the first one we're going to look at, if cared for properly, a tree has a 90% survival rate. So I'm going to do this in terms of success and failure. So success, 90%. Let's write it as 0.9, so that means failure is 0.1. If 10 trees are planted, what is the probability that 7 survive? That means how many would have to fail would be 3. So that means our total here is 10 trials. So this matches our experiment here because there's 2 outcomes. It survives or it'll die. There's a fixed number of trials. We're talking about 10. Each one is independent. The survival of one tree doesn't affect the other. And the probabilities are consistent. So it's always 0.9 and 1. So we start out with our combination. There's 10 total. We choose our successes, which we want 7 to succeed. The probability for success is 0.9. We want 7 successes. Our failure rate is 0.1, and we want 3 failures. And then we can just type this into our calculator. And you should get 0.0574. So about 5.74% that all 7 will that's only exactly 7 will survive. So let's see what the next one is. Oops. 8 out of 10 people will recover from a certain virus. If 7 people are infected, what is the probability that 3 people will recover? So again, I like to divide this up. We have success and failure. We want 3 people to recover in a group of 7, so 4 failure, so our total is 7. And 8 out of 10 will recover, so 0.8, 0.2, and excellent. We could, if we want a total, it adds to 1. So we start, there's 7, and we're choosing our successes, which would be survival, recover, 7 choose 3. Our success rate is 0.8 to the third times 0.2 to the fourth. And once again, you can just type that into your calculator and we'll see what you come up with. .0286. So about 2.8% of the time, 3 people will recover. But it's not too often that you want to know that exact number. I mean, we want as many people to be successful, to recover as possible. So often we'll be asked a question like this. What is the probability that at least 3 people recover? Well, that means we want 3 people to recover, 4, 5, 6, or 7. So again, we'd start this out, 3 people to recover. 7C3. Recovery rate is 0.8 to the third times 0.2 to the fourth. We'd add it to our recovery rate of 4 people, so this would change to 7. Choose those 4 to recover. Success rate is 0.8 to the fourth, 0.2, let's see, that would be 3 not recovering, plus 7C5 times 0.8 to the fifth times 0.2. Well, if 5 recover, that means 2 would not, plus 5C6, oops, not 5C6, 7, choose your 6 to recover, 0.8 to the 6th, 0.2, 1 wouldn't recover, plus 7, they all recover, which is great, 0.8 to the 7th, 0.2 to the 0. And this is a lot to type in, so you might want to calculate out each one individually and then add all those probabilities together.